This here is the Minimal 64X4 home computer designed by Karsten Herting, otherwise known as the YouTuber Slew4. Karsten designed this computer using solely logic chips, and it's a great computer to hack and get that retro homebrew computer experience. Karsten has published a whole video series on the Minimal 64X4, and I'd encourage you to watch it if this sort of computer interests you. However, this video is not about the Minimal 64X4 specifically. Instead, it's about this expansion card that I made for it. This card adds an exciting and fun new capability to the Minimal 64X4. But don't take my word for it, let's ask the computer to get this video started.
Hello, I am the 64X4 home computer. I can say things from this new module. In the next minutes, I will tell you how it works. Have a good time.
Hello! Yeah, it's been a while since I published a video. What can I say? Life happens. But I did have a project going for a while. Specifically, I was trying to add a speech synthesizer to my breadboard TTL CPU called the PD-1. If you're not familiar with my PD-1, I do have a video series on it, so I encourage you to watch it. However, I had to put that project aside for a while, and then when I finally came back to it, my PD-1 didn't work anymore. Could have been some wires got oxidized in the breadboard or something got pulled out. I don't know. I didn't have the patience to sort it out. So I had to look for a new platform to continue with my speech synthesizer project. I had been a fan of Karsten Herting's video series on his various TTL computers that he's been designing. They're all very well documented. He does a really good job at it. Ultimately, I selected his Minimal 64X4 computer for this project. Main reason being, it's a very capable computer, but it's pretty simple in design. And he's also done a very good job at documenting it. Finally, it also has a feature that is pretty critical to this project, which is it has an expansion port. So, decided to move forward with the Minimal 64X4 on this project. However, when designing the speech synthesizer circuit, I decided to use a TMS5220, and that presented some pretty unique design challenges. Specifically, the TMS5220 is referred to as a slow memory device. That is, its internal clock for operations like writing and reading to its internal memory is much slower than the host computer. In the case of the Minimal 64X4, the TMS5220 operates at a clock rate that is 50 times slower than Minimal 64X4's. This presents some challenges when the two interact with each other. In the 1980s, when the TMS5220 was used in various 8-bit computers of that era, the typical design approach was to pause the host CPU when the TMS5220 needed to read from or write to the host computer's data bus. I didn't want to design it that way. First of all, the Minimal 64X4 has no means by which to pause the CPU, so it's pretty much a no-go from the get-go. However, I also kind of consider that a lazy approach. I wanted to find a way to allow the TMS5220 and the host computer to operate independently of each other at their respective clock speeds. And when they had to interact with each other, the fact that their clock speeds were different didn't impact the other's operation. So that was the design goal for the circuit that you're about to see in this video. However, I also had another design goal. I wanted to design the circuit generic enough that it could be easily ported to other 8-bit computers, such as the Commander X16. So that's what this video is about, is I go into details about the design and then show you how I got it working. Before I do that, I do want to say, stay around to the end of the video. I have a giveaway. Specifically, I have a bunch of leftover Minimal 64X4 PCBs and speech synthesizer PCBs. If you're interested in that, I will be describing the giveaway at the end of the video. But first, let's get into how I designed this speech synthesizer circuit.
First, I think it's worth taking some time to go over what speech synthesis was in the first place. When computers were first invented, people wanted to get them to talk just like humans do. Talking computers would make a very natural way for people to interact with the computer. But the problem was that computers of the 50s, 60s, and 70s lacked the processing power that was required to make speech sounds directly. The first electronic speech synthesizers were developed in the 1950s. The early systems were crude, but in 1961, scientists at the Bell Labs used an IBM 7094 mainframe to encode and play back the song Daisy Bell. If you ever watched the movie 2001, A Space Odyssey, the makers of that movie made a nod to this bit of history when the antagonist of the movie sang this song. The technology quickly improved after this milestone, with chips being made that implemented linear predictive coding decoders. Texas Instruments got into the game in the mid-1970s by making their series of LPC speech synthesis chips, one of which was in the legendary toy, the Speak and Spell. Texas Instruments proceeded to iterate on their LPC chips, eventually making the TMS 5100 and the TMS 5220. These chips became very widely used in the industry. The TMS 5220 was used in many arcade games of the day, especially those made by Atari and Bally Midway. The 5220 was also used in the speech expansion cards for several home computers, such as the Apple II, the BBC Micro, and Texas Instruments' own TI-99 4A. It was in the TI-99 4A that I was first exposed to speech synthesis. I had a TI in the early 1980s, having bought it by saving up my earnings from my Detroit News paper route. I was fascinated by the speech synthesizer, and because of that experience, I am using the TMS 5220 in my speech synthesizer design today. Now, let's take a look at the technical details of the TMS 5220 chip. Here is the TMS 5220 pinout. Probably the first thing to note is the chip's power requirements. As with many TTL chips of the age, the chip requires plus 5 volts in ground. Note here that the manual refers to ground as V sub ref, or the ground reference voltage. Also note, this chip additionally requires a negative 5 volt power input. This may seem odd today, but back in the 70s and 80s, it was actually quite common for CPUs and complex chips to require multiple voltage levels. Nonetheless, this negative 5 volt requirement does present a design challenge for using the TMS 5220. The next pins to understand are the function control pins, the WS and RS pins at 27 and 28. These pins control how a host computer interacts with the TMS 5220. Both are active low. Bringing the WS pin low means the host computer wants to write data to the TMS 5220. And bringing the RS pin low means the host computer wants to read data from the TMS 5220. It is considered an error condition to bring both the WS and RS pins low at the same time, but on an improved version of the chip, the TMS 5220C, bringing both the WS and RS pins low at the same time would reset the chip. There are a number of timing details on how to use these function control pins, which we will get into later. Now, let me point out the pins that will be used that allows the host computer to understand the state of the 5220. First, there is the ready signal at pin 18. The TMS 5220 will bring the ready pin low when it's ready to accept input or provide output to the host computer. This pin will be central for coordinating data movement in and out of the TMS 5220. Another timing coordination pin is the interrupt signal at pin 17. The TMS 5220 will bring the interrupt pin low whenever there are conditions on the chip that the host computer needs to react to. To read data into or out of the TMS 5220, these 8 bidirectional data bus pins are used. Depending on how the host computer sets the WS and RS signals, these pins will either assert a value to the data bus or read a value from the data bus. The TMS 5220 requires an external clock signal, which is provided to the OSC pin, which is pin number 6. Note the clock requirements of this chip are relatively slow, requiring a 640 kHz clock. Normally this clock is provided by a tuned RC circuit, which we will review later. Then there is the business end of the chip, which is the speaker pin. The audio signal that the TMS 5220 produces comes out of this pin. Finally, there are a large number of other pins I haven't yet described. Collectively, these pins pertain to connecting the TMS 5220 to what is known as speech ROMs, which were specially made read-only memory devices, such as the TMS 6100. These ROMs were designed to be a companion to the TMS 5220. These ROMs simplified the software that would use the TMS 5220 by being able to tell the chip to speak the sounds encoded at a given address on the speech ROM. It is difficult to get these speech ROMs today, and they do have limited vocabulary, so I'll be ignoring this interface in today's video. However, Of these speech ROM pins, there is one that we are going to be using. The ROM clock pin represents a clock signal that is 1/4 of the externally provided clock signal. We will use this pin to measure and tune the external clock without worrying about our oscilloscope measuring probe altering the RC circuit being measured, and thus changing the clock signal being produced. This will allow us to more accurately get the target internal clock of 160 kHz. Before I get into the details of the design I used for the speech board, let's go over my goals. The obvious design goal of this project is to get a circuit running with the Minimal 64X4 that will enable it to use the TMS5220 speech synthesizer. Beside that, I had another design goal, to not require the CPU to pause while the TMS5220 is processing inputs and commands. As I said, most 80s era computers that used the 5220 did use the ready line to put the CPU into a wait state, not processing anything until the TMS5220 was ready to proceed. I felt it was a waste of CPU cycles, and I would rather enable the CPU to do other processing while the TMS5220 is busy processing an input. So that second goal is the main design challenge here, as it runs counter to the standard way most 80s era computers implemented support for the TMS5220. Nonetheless, I think it's doable, and doing so would open up a rich set of design options when using the board. Finally, I want to be able to use my own audio recordings when generating an LPC that will run through the TMS5220. This is just one of those because I can type of requirements, but I do think it would be cool to hear my own voice come out of the 80s era tech. Here is a schematic of the TMS5220 speech synthesizer board I designed for the Minimal 64X4 home computer. There's a lot going on here, so let's start with the expansion bus connector to the Minimal 64X4 computer. Here you see it has 32 pins, which all but one are used. There are 16 pins for the address bus, 8 pins for the data bus, power pins, the reset line, and the system clock. The RO line is an active low line that, when asserted, indicates that the memory value at the address indicated in the address bus should be written to the data bus. The RI line is also an active low line that, when asserted, indicates the value on the data bus should be read into the address being written to the address bus. The RI and RO lines are used across the entire address space of the Minimal 64X4 computer, meaning they are used for accessing RAM, ROM, and any memory map devices. This speech synthesizer card is a memory map device. If you take a moment and think about things, you might realize that there is a potential for bus contention. Specifically, if more than one device writes data to the bus when the RO line is asserted, that is, if two memory devices respond to the same address, then there might be contention on the bus. To prevent an expansion card from creating a bus contention, the INH line, or the memory inhibit line, is added. When the INH line is asserted high, the Minimal 64X4 RAM and ROM chips are not activated, and thus cannot write to the data bus. So, when an expansion card wants to write data to the data bus, it needs to assert the INH line. On the left side here, you see there are two 74HCT688 8-bit value comparators. These are used to check the address bus for a value that represents the memory mapped address of the expansion card. When the address on the address bus is in the targeted range, then the equality output of the second 74HCT688 will be asserted. This output is picked up by this ATF22V10C programmable logic device. You will also note that there's a large number of lines being inputted into this ATF22V10C. This programmable logic device is being used to manage the state of the speech synthesizer board. To understand what that means, let's take a look at the timing diagrams of the various operations for the TMS5220. Here is a timing diagram for writing information, whether it be a command or a byte of data, to the TMS5220. To start a write cycle, you bring the write select WS line low. Once the WS is brought low, the TMS5220 will configure itself to receive data, and when it's ready, it will bring the ready line high. Once the ready line is high, after some delay, the TMS5220 will be ready to read the contents of the data bus. Here's the first important consideration on the issues with timing on this chip. Note that the T sub WS-DV time indicates how long the TMS5220 takes to start reading the data bus after bringing the ready line high. This value is 7 microseconds. It doesn't seem like much, But consider that the minimal 64x4 computer's clock is 8 megahertz. That means each clock cycle is 0.125 microseconds. It will take the TMS 5220 about 56 clock cycles from the time that it says it's ready to read the data bus until it is actually ready to read the data bus. Similarly, look at the amount of time that the ready line will be held high by the TMS 5220, as indicated by the T sub WR parameter. It is minimally 18 microseconds. During this time, the data bus must maintain the value that needs to be written to the TMS 5220. When the ready line is returned to low by the TMS 5220, then the data bus can be used for other things. That 18 microseconds of hold time translates to at least 144 clock cycles on the minimal 64x4. Given that the average instruction on the minimal 64x4 is about 4.3 clock cycles, that means at a minimum, the value we wish to write to the TMS 5220 must be held on the data bus for 33 instructions. In the 1980s, this slowness problem was solved by a very brute force manner. Consider the early 80s computer, the Texas Instruments TI-99/4A, which had a speech synthesizer add-on you can plug into the side of the computer. Here is the circuit design for the TI-99/4A's speech synthesizer expansion box. Here is the TMS 5220 using the expansion. Notice how the ready line is used to drive this transistor, which in turn is set up to pull pin 12 of the TI-99/4A's expansion bus low when the ready line is active. This pin 12 of the expansion bus connects to the TI-99/4A CPU, the TMS 9900. Specifically, it connects to the ready pin of the TMS 9900. When that pin is brought low, the TMS 9900 enters a wait state and suspends all operations until the ready line on the TMS 9900 becomes high again. The implication here is that the TI-99/4A CPU simply pauses operations until the TMS 5220 is done reading the data. Many other computers of the era had the same design. As I said, I didn't want to do this in my design. Probably the biggest issue is that the minimal 64x4 does not have a means by which I could pause the CPU while the TMS 5220's ready line is high, but also I want to see if I can make the TMS 5220's processing independent of the CPU, any CPU. So given that information on the TMS 5220's timing challenges, let's go back to my board schematic and explore the design I put together to bridge the timing differences between the TMS 5220 and the minimal 64x4. First, note that we use a pair of 74 HCT74 flip-flops. These flip-flops are used to drive both the WS and RS pins on the TMS 5220 independent of the host computer's clock cycle. Also note that the host computer's data bus is not connected directly to the TMS 5220. Instead, the data bus is moderated by a pair of 74 HCT374 8-bit flip-flops. One for capturing the data from the data bus and writing to the TMS 5220, and another for capturing the data from the TMS 5220 and writing it back to the host computer's data bus. All of these flip-flops are then coordinated by the logic I have programmed into the ATF22V10C programmable logic device. I'm not going to go over the details of the PLD logic I programmed into the ATF22V10C, as you can review that in my Git repository. But I will describe the sequence of events that are needed for the host computer to send a byte of data to the TMS 5220. First, when the address bus is set to the memory mapped address of FEZ0, the 74HCT688 will assert this mmap line, and the M0 and M1 address lines will be at 0. Furthermore, to write to the TMS 5220, the host computer's RI line will be asserted. The ATF22V10C's programmable logic will then assert this WS clock line, which is the clock line that is driving the WS flip-flop. This flip-flop in turn activates a low signal on the WS line to the TMS 5220. This tells the TMS 5220 that we want to write data to its data lines. At the same time that the WS clock line causes the WS flip-flop to set its state, the WS clock line is also used to cause the data bus input 74 HCT374 flip-flop to load the contents of the host computer's data bus. Because of this, the expansion board can capture and hold the data bus value the host computer is trying to write to the TMS 5220, thus allowing the host computer to move on to other things while this flip-flop is holding the data bus value for the TMS 5220. Furthermore, this WS line to the TMS5220 also drives the output enabled on the 74HCT 374 octal flip-flop used to buffer the data from the host computer's data bus. So the buffer data will be held and written to the internal data bus on this board the whole time that the WS line is held low, even as the host computer moves on to other things. This is where the slow memory issue of the TMS5220 plays out. As previously discussed, the TMS5220 will take several host computer clock cycles to read in this data, and its data lines need to be held to the desired values the whole time. By using this flip-flop to buffer the data, holding the data lines active for an extended period of time is possible. The third step here, in response to the WS line being asserted, the TMS5220 will drive the ready line high. When this occurs, the ATF22V10C is programmed to wait until the ready line subsequently transitions from high to low, which indicates that it's done with processing the input data. When a ready line returns to low, the ATF22V10C then asserts the WS RST line, which is the reset line for the WS flip-flop. This brings the WS line high, which tells the TMS5220 that we are no longer writing data to the internal data bus on the speech board. This also turns off the output enable on the 74HCT 374 octal flip-flop that was buffering the data to be written to the TMS5220. In this way, the WS line is asserted onto the 5220, indicates it is done with reading the data from the buffers, as indicated by the ready line. Finally, the whole time the sequence is occurring, the ATF22V10C asserts the busy line for the board, which can be read by the host computer at address FEC2 via the 74HCT245. This then allows the host computer to query the board to determine if the TMS5220 is done with processing the data. A similar set of logic is used to read the values from the TMS5220 using the RS line and the data bus output flip-flop here, all adhering to the required sequencing and timing of the TMS5220 for reading values. You will note that I also have other signals reported by the 74HCT bus driver writing to the host computer's data bus. Probably the most important status bit exposed here is the busy line I already mentioned, but it also reports the TMS5220 interrupt pin. The TMS5220 interrupt pin indicates that there is something up with the TMS5220 that the host computer needs to pay some attention to, most notably that the internal speech data buffer is running low. Normally this line would trigger an actual CPU interrupt, but since the Minimal 64X4 does not support interrupts, this pin status will need to be pulled. You will see later that this is used to help control the interactions the host computer has with the speech expansion board. Finally, note this negative 5-volt converter in the upper left of the schematic. This is a ready-made power inverter that is being used to convert the host computer's positive 5 volts into a negative 5-volt line, as required by the TMS5220. I got this converter from a seller on eBay, the link of which can be found in the build of materials provided in the GitHub repository for this project. This is the fully built TMS5200 speech synthesizer board for the Minimal 64X4 computer. As you look at it, you can see the various chips that we discussed when we reviewed the schematic. Here's the TMS5200. This is the ATF22V10C. These are the various flip-flops and the line buffer. Here is the negative 5-volt converter. If you look closely at the schematic, you'll notice that there is this RC circuit that feeds into the OSC pin on the TMS5200. This RC circuit is used to create a clock signal going into the TMS5200. The vibrations from the RC circuit is the clock signal that the chip will use. However, this clock signal needs to be precise. The TMS5220 will downsample and convert this clock signal into a nice square wave and then use that internally for the various operations that it needs to do. That converted clock signal is then fed out of this ROM clock pin on the TMS5220. We need to make sure that the RC circuit is tuned such that the output clock signal from the ROM clock pin is exactly 160 kilohertz. If this clock signal is too fast, the speech sounds that the TMS5220 will produce will be too high pitched. And if this clock signal is too low, then the speech sounds will be too low of pitch. So that's our task, is to tune this RC circuit to produce the right input clock signal. So to tune this circuit, we will adjust this potentiometer until the ROM clock pin emits a 160 kilohertz signal. You can see here that I have this board connected to power. The power is being distributed by this breadboard here so that I can also get the same ground signal to go into my oscilloscope probe. Let me turn on the oscilloscope and we can start the test. And I'll turn on the power to the board. And now this board is powered with 5 volts. The RC circuit is outputted from this resistor here. So if I put the oscilloscope probe on the resistor lead, you can see a nice triangle wave. Frequency is at 233 megahertz. I think that's going to be too fast. We can verify that by looking at the ROM clock output. Now, on this board design, I did bring that ROM clock output out to this test point here, so that's easy to work with. So if I just put my thing on the test point, and you can see the output frequency from the ROM clock is at 876 kilohertz. So we do need to adjust this. So the thing to do is to adjust this potentiometer. That's the wrong direction. Let's go make it slower. Okay, we're at about 200. A little bit more to go. There we go, 160 kilohertz. Now, if you look at the RC output, you get about 422 kilohertz. My understanding is the TMS 5220 downsamples this input by about a factor of 4. So the reason why you're not getting exactly 4 times 160 kilohertz is because the probe of this oscilloscope does interact with the RC circuit such that the frequency changes. If I had 2 probes, I don't have 2 probes on this oscilloscope, but if I had 2, probably could show that. But in the meantime, just verify we're still at the right frequency. 160 kilohertz. We're good. Okay, before moving forward and connecting this to the Minimal 64X4 computer, let's review the driver code I had to write in order to allow the Minimal 64X4 computer to interact with this board. One important note is that I am using the open source assembler named BespokeASM in order to build the Minimal 64X4 software in this project, rather than the assembler provided by Karsten in the Minimal 64X4 project. The reason for this is that Karsten's assembler fits with Karsten's overall project theme of keeping things minimal. As a result, the Minimal 64X4 assembler is missing some key features that make more complex projects like this one more manageable. Most importantly, the ability to break your code up into multiple files. I want to write the speech boards driver once and just import that code into any project that's going to use it. The Minimal 64X4 assembler does not allow you to do this. But the BespokeASM assembler does allow you to include files using the include directive. There are other features like the use of namespaces, which are all used in this project. Finally, BespokeASM has a feature that anybody who does a lot of coding will appreciate: the ability to generate syntax highlighting. So this code is Minimal 64X4 code, and the highlighting you see in the Sublime text editor is done through a syntax highlighter that is provided by the BespokeASM assembler. Clearly, this is much easier to read than if it was just plain black and white text. Okay, let's go over to the library that I had to write in order to enable using the speech synthesizer board that I created for the Minimal 64X4. The first thing the driver needs to do is to initialize the TMS 5220. This happens once at the start of each program that is actually using the speech synthesizer board. This code here, the subroutine called speech_init, implements the documented protocol for initializing the TMS 5220. The important subroutines to understand what's going on here are these speech send command subroutine and the wait on speech board busy. So let's explore those real quick and understand what they are doing. The speech send command subroutine is a pretty simple subroutine. It actually calls the wait on speech board busy subroutine itself. What that function actually does is wait until the speech board reports that it is not busy with doing something. As you recall from the schematic review that we did, the ATF22V10C generates an output called the busy output, which indicates whether the board is doing something, such as reading some data into the TMS5220 or writing some data out of it. What the wait on speech board busy subroutine does is simply wait on the busy bit, as reported in that register, to go to 0. Once it does, then it returns. Now, you may look at this and say, hey, one of my design's goals is to be able to write the software such that while the TMS5220 is busy doing stuff, the host computer can go off and do other things. And by implementing this, essentially this busy wait right here, I'm doing something that's no better than pausing the CPU as was done in the 80s era computers. My response here is that this implementation is pretty expedient, and I am not able to spawn threads on the Minimal64X4, given the fact that there is no means by which to do that in the way the CPU is built. Furthermore, if the Minimal64X4 was built to be able to respond to interrupt requests, I could possibly have this function operate using an interrupt and thus allowing the host computer to work on other things while waiting for the board to no longer be busy. Admittedly, I chose the more expedient path rather than redesigning the Minimal64X4 to allow me to use some level of multiprocessing. Getting back to the speech send command function, once the wait on speech board busy subroutine returns, what the speech send command function does is load the command that was actually passed to this function on the stack into register A, and then store that value to the speech command register, which is the address on the board, which will write the host computer data bus into the flip-flops that in turn write values into the TMS5220. This will actually initiate the TMS5220 write process, which we reviewed earlier in this video. The second thing to know for this driver code is how it initiates speech. As pointed out earlier, this expansion card only implements speech using external data. That is, there is no internal speech ROM attached to the TMS5220, so all speech data that is transferred to the TMS5220 comes from a buffer that is held on the host computer's RAM. The process for sending speech data to the library starts with the speech start method. The TMS5220 only has a 16-byte buffer, so you cannot send the entire buffer from the host computer at once. Instead, you need to send the first 16 bytes of your speech data to the TMS5220, and then it will start speaking using this initial data. As it consumes that data, the TMS5220 will set a flag in the status register indicating when its internal 16-byte buffer is half empty. And it will also assert its interrupt pin on the TMS5220 in order to indicate that it had a significant internal state change. Since the Minimal64X4 does not have interrupt support, the speech driver software instead periodically queries the board state to see if the interrupt pin is asserted. This is done in the speech update buffer method right here. If the interrupt pin is asserted, then the library queries the TMS5220 internal state register to see what has changed. Here the library will see that the internal buffer to the TMS5220 is half empty. At that point, the host computer can send the next 8 bytes of the speech data. This process repeats continuously until all the speech data has been transferred to the TMS5220. The TMS5220 is free to perform other work while it is periodically checking for the interrupt pin state. That is what this code is doing here. I've actually broken that process up into 2 parts, loading the initial 16 bytes here in the speech start function, and then a subroutine to check the speech board's interrupt status to see if another 8 bytes can be loaded. This truly allows the host computer code to be written such that it can do other things while the TMS5220 is consuming the next 8 bytes of data in its buffer. I in fact used this approach to bring speech to an existing game on the Minimal64X4 without the speech processing interfering with the playability of the game. That game was the Space Invaders game that Karsten originally wrote for the Minimal64X4. The way I integrate speech into this game was to first initialize the speech library when the application starts. Then, in the main loop of the game, I periodically call the speech update buffer function, which checks to see if the TMS5220 needs another 8 bytes to be sent to its speech buffer. If there is no speech happening at this moment, then nothing happens when this function is called. If there's speech occurring and the buffer is half empty, then more data would be sent to the TMS5220 so that the speech sound can continue. Then the only other thing I needed to do to integrate speech in here is to initiate a speech sound when a certain event occurs within a game. An example of that is when a new level starts in this game, I play a sound, and here's the code that I use to play that sound. Now the speech data that is being used throughout this game is actually in this code here. It's all the way at the bottom of the file, and this is what it looks like. Here is an example of a buffer that is used that I will send to the speech library for the TMS5220 to speak the contents of what this buffer represents. Okay, that's how the speech library is written. Let's go see it all in action. Okay, it's time to put this TMS5220 expansion board into the Minimal 64X4 computer. One thing you'll notice off to the side here, I have a custom designed expansion bus for the Minimal 64X4. You'll notice some bodges on it, specifically this resistor here and some jumpers. This was done because the design, basically I forgot to install some pull-down resistors into the design. The actual schematic that you find in the repository for this project has been corrected and actually has the pull-down resistors. I just haven't sent it off to the PCB house yet, waiting to the next project just to do it all at once. Okay, so let's go ahead and get this installed. Put this in the expansion bus. Turn on the speakers. Turn on the screen. And turn on the computer. When the Minimal 64X4 comes up, it always comes up in a random state, so you have to reset it. And there, it's good to go. Okay, so I did mention at the beginning of the video that my goal is to record my own voice and then play it on the TMS5220 through a player that I've built for the Minimal 64X4. So let's go ahead and get that done. First, let's actually record a sound in this auto recording program. Doesn't have to be a fancy sound. We'll just record a pretty simple statement. This is the Minimal 64X4 with a speech synthesizer. Before we encode this into LPC, let's actually clean up the sound a little. I like to cut off the beginning and end silence, and then also apply a dynamic compressor. This is the Minimal 64X4 with a speech synthesizer. Okay, that sounds okay. Let's go ahead and save that. And then let's go to actually turn this into LPC encoding. To do that, I'm going to use a program called Python Wizard. Python Wizard is an open source program that you can get on GitHub. The link to it is down in the description of the video below. To run it, the command line looks a little bit like this. All these options allow you to tweak how the audio is converted into LPC encoding. I'm not going to go over the details of that here. The documentation for the Python Wizard has pretty good explanation. I did find that the settings that I have here are good for most generic use cases. Since this is just a quick demo, I'm not going to worry about making it perfect. And here is the LPC encoding expressed as a bunch of hex digits. I'm going to want to copy this because we're going to have to send it over to the Minimal 64X4. And I'll go to my terminal with the Minimal 64X4. I did write a program called LPC Play. This program is available in the software of the project repository. What this program does is allows me to send the Minimal 64 a bunch of LPC encodings, much like the ones we just created, over the serial connection, and then it will play the sound represented by that data on the TMS5220 for us to hear. So let's see how this works out. I'm just going to paste to send it all. And according to the instructions, the final character to terminate the sending is the escape.
This is the Minimal 64X4 with a speech synthesizer.
There you go. It worked great. Normally what someone would do when they're designing sound for the TMS 5220 is tweak those parameters that I just talked about for the Python wizard, or also tweak the way that the sound was recorded, maybe possibly apply a few other filters so that it sounds good. To give you an example of that, I have some professionally encoded sounds from back in the day for the TI-99/4A in this program that I call Speech Demo.
Hello.
That's actually me.
Daisy, Daisy, give me your answer to.
An example of singing sound with the TMS 5220. Okay, next one.
To begin.
That was the sound from the TI-99/4A game called Parsec. Basically, it was infamous amongst TI-99/4A enthusiasts. And at the beginning of the game, that sound was played. Okay, last one.
Better luck next time.
This is a sound that I found in a Arduino library that emulates the TMS 5220 on the Arduino. It had a few sample sounds, and so I tried them out in this demo program. Okay, now I have a keyboard attached to my Minimal 64X4 computer rather than my laptop. And so what I'm going to do now is, remember earlier when I was showing off the library, I mentioned that I modified Karsten's implementation of the Invaders game to actually have some speech sounds associated with it to give you some more lively playing. So let's go ahead and try that out, see how that works. I called the game actually SP Invaders. SP Invaders, plural.
To begin.
As you can see, I had the program play that Parsec intro at the beginning of this game too, just because it's a call out to my childhood playing that Parsec game all the time. Let's go ahead and play it. So some of these sounds that you're hearing came from that Arduino library that I mentioned earlier. They had some example sounds. But some of these sounds are actually my daughter. She graciously allowed me to record her so that I can use as a sample. Specifically that bang.
You can't touch me.
Let's go get that guy.
Oh.
Okay.
You can't. Looks like you lose.
Yes, the game also mocks you when you finish.
Okay, yes, I got the TMS 5220 working on the Minimal 64X4 computer. This was a fun project for me. When I was a kid and I had a TI-99/4A, getting that speech synthesizer was just magical. Hearing a computer talk was amazing. And so that was part of the motivation of actually doing this project in the first place, was to recreate some of that magic I felt as a kid. If you want to do the same, as I said at the beginning of the video, I have a giveaway here. I have a bunch of extra PCBs from the Minimal 64X4. When you order PCBs from a PCB manufacturing house, you have to order a minimum order. I only really needed one, but I had ordered 5. So I have 4 that I'm willing to give away to anyone who's interested in having them. All you need to do is contact me at the email address that's at the top of the screen right now and send me your address, and I'll calculate shipping. I ask that you pay for the shipping for me to send it to you, but otherwise the board is free. So contact that. I'll also throw in a speech synthesizer board if you want to create your own expansion for this. The chips that you need, you will have to find. Karsten does document a bill of materials for the Minimal 64X4, and the chips for the speech synthesizer board are documented in the bill of materials in my GitHub repository. So again, if you're interested, contact that email address, send me your address, and I'll be happy to send it to you. So that's it for today. I hope you enjoyed this video. If you did, I encourage you to subscribe to my channel. As I mentioned at the beginning, I don't publish often, so if you subscribe, you'll get notification when my next video comes out. Until next time, thank you for watching, and goodbye.
You can't touch me! Oh!